And hello, welcome everyone to this FreeCAD, Salome FreeCAD OpenFOAM kind of a tutorial series. So welcome back. In the last video, I was struggling to finish within the time limit of 20 minutes-ish. A case with added boundary layers. So I wasn't finished with that one quite yet. So it is in this heat exchange video tutorial. Did I put it here? Oh dear, I have. Okay, I was messing around with the files. Okay, okay, so yeah, I've been messing around with the files. You know what? Let me generate the files and I'll be right back. I'll fast forward this process. Okay, so I'll fast forward to at least give you the steps. I have this mesh and I applied. Okay, I applied a moderate fineness with max size 10, min size of 1. That's how I do it. And I have a viscous layer hypothesis with surface offset of smooth. Excuse me. Total thickness of 2 millimeters, 3 layers, stretch factor of 1.1. Okay, and I use the netgen 1D, 2D, 3D algorithm. Okay, so very simple. Because we moved the shape out, we have gotten rid of it, the funny shapes in the middle in the debugging process. So now it's functioning exactly as it should. So I'm just going to quickly export this UMV file to the heat exchanger video tutorial. So I put heat exchanger with boundary layer. Okay, so I'll export it directly to the OpenFOAM directory instead of the salome directory to save time. Okay, so let's go to heat exchanger video tutorial. I'll clean this up and I'll use this here and I'll go into the I don't have a salome style free. Okay, whatever. Let me copy. Oh, never mind. I'll show you the steps. Hold on. Okay, so let's go. Heat exchanger video tutorial. I'm going to start copying the FreeCAD into a salome mesh gen. Okay, salome mesh gen. What will it contain? It'll all clean first. I will restore the 0 directory. Okay, I'm not going to run block mesh or surface feature extract or snappyx mesh. I am going to run ideas UMV to foam. Ideas UMV to foam. And heat exchanger boundary layer.unv. Heat exchanger boundary layer.unv. Okay, after that heat exchanger boundary layer.unv, I can do transform points. I can do the polymesh override. Then I will do a touch heat exchanger.foam heat exchanger, and of course I used the wrong tool in the last video. It should be the boundary should not be, the tool used should not be what do you call that, create patch, but it should be change dictionary. So let me go to the polymesh file if it's there. Oh, it's not there. Let me do ideas UMV to foam of this salome file, and I'll quickly make the patches. Now go to polymesh and I'll go to boundary. Okay, I'll copy all these entries here. Okay, I'll delete most of them actually. But yeah, let me delete all of this. Okay, so I'll paste, and the tubing outlet hemisphere. Okay, outlet I don't need because this one is by default patch. Okay, so this is how I did. I'll delete all the end faces and everything because depending on how fine the mesh is, the numbering will change of the start and end faces. Okay, so I'll change the inlet, outlet, and the tubing to wall. Alright, inlet, outlet, and tubing to wall. And I will go to salome gen and I'll type in change dictionary. Okay, change dictionary. Okay, let's do change dictionary. Alright, so you'll change the inlet hemisphere, outlet hemisphere, and tubing to wall. So okay, change the inlet, outlet, hemisphere to all this to wall. I can run a check mesh. Of course, mesh is okay. So the salome mesh is okay. I hope I can run transform points as well. Okay, transform points, and I'll scale it down by a factor of 1,000. Okay, so that's in my salome mesh gen script. Scale it down by a factor of 1,000. I can of course do the poly mesh as well, but I'll just run pimple foam first to see if it works. Okay, where is it? Okay, I forgot to copy original file to 0 and do a pimple foam. Okay, cannot find patch field entry for inlet. Shucks. Let's see. 0.original VIU. Oh, it's still the old patches. Okay, so I'll need to change all these old patches, and they are inside here. I'll copy this 0 original file to yeah, I need to name the patches all correctly in the boundary conditions, but I'm not going to show you that part because I've already done it in another video. So let's go to CD heat exchanger video tutorial. Okay, and go to 0.original VIU, and this is what should be there. Alright, so the outlet, inlet, tubing, everything should be here. This should be named as such. So I have the outlet patches. I've discussed this in the last videos. I also tell you how to do the inlet patches as well. I also have this extrapolate profile here, which I turned it off, meaning to say that your inlet flow will be a plug flow. Apparently this actually contributes to the stability of the problem. I mean, of the numerical solvers. This was actually one reason why when I played with salome meshes, it could not converge. It was because of this extrapolate profile option. So you just leave it as plug flow at the inlet. Okay, so because this extrapolate profile, normally when you have this flow rate inlet velocity, it will give you an inlet volumetric flow rate into the control volume, into your mesh with this volumetric flow rate, and it will give you a plug flow. Of course, you have the option of actually looking at the velocity profile downstream, and then you extrapolate the that velocity profile to your boundary condition. Unfortunately, that itself causes the solver not to quite converge very well, so I'm taking that out. Okay, so this is what it's like. I'm going to CPAR0 original into 0 and run pimple foam. Okay, still has a problem. Let's see. Cannot find patch field entry for inlet. Oh, I'm running it from the pimp. Okay, let me do it all clean again. IDS UMV to foam, heat exchanger boundary layer dot UMV. Okay, let me run the salome mesh gen script. Okay, I also do the poly dual mesh, but of course this actually fails the mesh check, but let's see whether it works anyway. Alright, so it does work. Okay, and it's converging well-ish. Okay, but this actually, yeah, okay, at least the thing runs, but it's not converging as well. Maybe because the poly dual mesh is there, I am not very sure, but I will just leave this thing as experimental. But that's basically how to get the Salome thing running. Okay, I would move this. I would change the name to heat exchanger Salome BL experimental. Okay, I have a Salome case that's working. Heat exchanger. Oh dear, I spelled it wrong. Heat exchanger. Okay, heat exchanger Salome BL experimental. Okay, so I have a heat exchanger Salome file. And then this one, it's just a basic case where there's no boundary layers, but the solver is stable enough, so it's actually running pretty well, and it's doing with a poly dual mesh. So I can just do a run parallel script here. Okay, and it will start to run in parallel. Okay, so if you go to heat exchanger Salome, alright, and you will see all the files there, and you can look at pimple foam. Okay, it will show you that it's running very well, and actually it converges pretty quickly. So good. Yep. So I mean, there's a tricky thing about meshing is that you never know. I mean, playing with a mesh that is stable, I mean, it takes a lot of trial and error. And the one that I got it to work was without the meshing. I mean, without the boundary layers. And what I did was to give it a custom fineness. So what is fineness about? It will give you a number of segments per edge, number of segments per radius. I'm not going to go into that. But it gives you the growth rate here, which you can adjust. So fineness will tell you what this growth rate is. So you can imagine in the center of your pipe, you'll have very coarse meshes, and towards the edges, towards the surfaces, you have a smaller mesh, which is what you should expect. So when you have the average size of the mesh, all right, if you have an average size of the mesh just adjacent to the wall, maybe this is 1 mm in diameter. So if you say the growth rate is 0.3, then it is 0.3 times this next mesh will be 0.3 times of this 1 mm. So this is growth rate. Okay, so this is growth rate. So this will be 1.3 mm, and then you just keep multiplying by 0.3. Now that would actually allow some irregular shape mesh to be in the middle, because this is a complex shape. This is a really complex shape, and then you have some meshes in the middle that are a little bit more complicated to deal with, and therefore you will not have as good a result. Okay, you will not have as good a result. Okay, some of those meshes in the middle are a little bit irregular shape, so that can actually lead to some problems. So if you want the meshes to be so-called smaller, alright, smaller in general, you can actually change this growth rate by using a custom fineness over here. I shifted it to 0.1 for the non-boundary layer case, and now of course I ran it on a poly dual mesh, and that actually enables it to run pretty quickly. So if you take a look at the heat exchanger Salome here, so yeah, processor 0, it's already gone on to 0.24 seconds, so you can see it's very fast. Okay, so I'm just going to stop because I know that case will work, right? That case will work. Okay, so So I'm going to stop here. Okay, and I'm going to do a all clean, and I'm just going to do an all clean here. So I'm just going to upload all of this into GitHub. So let me check whether there's any extra files I don't want hanging around. So I just do /sh star. So I can go to heat exchanger salome and do all clean. Actually nothing too big. 13 max and 15 max. There isn't too much of an issue here. Okay. Okay, then I can do a git status. Okay. And these are changes not stated for commit. I want to untrack everything, so I'll just do a git reset. Alright, git status again. Let me check. Git log one line. Git log one line. Alright, git reset 925 fcae. Okay, and clear. Okay, git status. Okay, it looks like I have some files that I don't really want hanging around. Let me see whether git log one line, git reset fb22 f36 fb22 f36. Okay, git status again. Let's see. Alright, I need to reset this a bit. I'll fast forward this, you don't have to see this. Okay, so resetting it even one commit earlier, that's fine. I got to delete everything I don't need. So let me just do a git add. Okay, git commit basic heat exchanger with salome, no BL added, along with some other files. Okay, so I'm going to push this, and it's probably not going to let me push, but I'm going to try anyway. Okay, git push force. Yeah, I meant it with 2 dashes. Okay, good. Now it's uploading everything to Git. Alright, so yeah. So now you will have access to the files in by looking to the bottom of the YouTube video. You should see my OpenFOAM Intermediate playlist and GitHub repo. This is where the repo is. Okay, go to Intermediate Plus and you will see all the files here. You'll see some basic shapes here, heat exchangers. These OBJ files are here. If you want the salome files, they will be in here when you have these UNV files. So they are available for you to play around with, and there are lots of other settings you can play around with salome. Besides adding boundary layers, you can adjust fineness as I just showed you. You can adjust the fineness, which is actually the growth rate from the wall. Yeah, so that's what it means. It doesn't mean that yeah, it means that there's a less difference between the you can change the relative rate of difference between the maximum and minimum sizes. Of course, you can do lots of other stuff as well. There are other algorithms that you can play with, but I've already showed you the basic ones. Tetrahedral meshing with boundary layer addition. After that, you can just run your own polydual mesh. If the stability permits and everything, you can run that. And you can play with such other things as second order, for example. Okay, but that actually makes the mesh a lot smoother. Okay, okay, I wasn't intending to show that, but anyway, this is just some extra. Okay, but you can run it for yourself and you just play around with the settings. You can see second order is a bit smoother, I think. Yeah. Did I do second order? No, I did not do second order. Okay, never mind. Okay, since it's here, I need to compute this. Okay, so this is second order, what it looks like. You see, you see those triangles are now a little bit bent because they put different shape points over here in the center of the triangles. So that's what second order means. It allows these triangles to be slightly deformed because you put another way to shape. You put instead of strict tetrahedrons, you allow the triangles to be slightly deformed and thus fit your shape a little nicer. And that's what second order stuff is about. Anyhow, this is Salome, and you can play around with the settings and do encourage you to do it. Edit the hypotheses. You can even segment your mesh to make it finer at some places and not so fine at some other places. Those are a little bit more complex, and I believe there are YouTube videos doing that. And unless there's a reason to do it, I don't think I'll be going through it. Okay, if you go to YouTube, you search this thing called Salome mesh submesh, you will see this thing called Salome module meshing the bracket. This is a very good video by Open Cascade. They'll basically show you how to mesh different regions of the Salome mesh with different fineness. Yep. Let me see. Yep, this is the video. Okay, so I'll not do a different one unless absolutely required. But what I've showed you is to roughly work with Salome. Know how to get around with Salome, know how to do tetrahedral mesh, know how to do boundary layer addition. Of course, getting the simulation stable is a whole another ball game altogether, and that actually takes a lot more experimentation and fine tuning. So you got to play around with the mesh. You have to troubleshoot, but that's the name of the game when it comes to CFD. There's no running around with it. Okay, time is up. Yeah, there's no running around. You can't run away from these problems. You have to solve it on your own. I can't, give you all the solutions possible, but what I do have, I will share, like the basic usage of Salome, and yeah, perhaps some pointers on how to make the simulation more stable. Alright, so there's no one size fit all answer, so I'm not going to keep posting how to tweak stability, though that may be helpful, but I'll really show you some tips. So okay, I've gone on long enough. Thanks for watching. I'll see you guys in the next video. Hopefully we can talk about more other interesting things and mesh more. We'll see. Yeah, we'll see whatever else is needed or whatever else I have time for. Okay, see ya.